This is video 1 for the invisible light unit. So for this unit, I want you to be able to discuss uses for infrared radiation. I want you to be able to explain how sunscreen lotions and black lights work. I want you to be able to explain how microwave ovens heat food. And I want you to be able to discuss different types of medical imaging technologies. So let's begin with infrared radiation. Infrared light, sometimes it's commonly called IR. It's a wavelength that is longer than visible light. The longest wavelength of visible light that we can still see is right around 650 nanometers. And that would be right around a very, very dark red. Infrared, or IR, has a wavelength from 650 to around 20,000 nanometers. Its wavelength is much, much longer, so its frequency must be lower. So when we take a look at the electromagnetic spectrum, we see that we have our visible light, which goes from around 400 nanometers to around 700 nanometers. Like I said, 650, that's kind of like an average. Sometimes it goes down to 700 or up to 700. But right above that, we have our infrared. Now, infrared radiation will warm up objects that absorb them. So you can think about heat lamps for this. Now, you emit infrared radiation because you are warm. The electrons in your atoms shake since they are not at absolute zero. So they're a constant state of motion. That's the kinetic theory. And a shaking electron will have a shaking electron field, and also a moving electron will have a moving or changing magnetic field. So these shaking electric and magnetic fields create an electromagnetic wave. The result is that everything emits light, except for things that have a temperature at absolute zero. So everything glows. However, most things emit so little light, we don't notice it. Of course, we don't notice it if most of the light is a wavelength that's invisible to our eye. So we can start talking about heat radiation and temperature. So the amount of heat radiation, we can calculate it using some laws of thermodynamics. So here's a graph, and we have temperatures corresponding with specific wavelengths, and the increase of intensity of the temperature and the decrease of peak wavelength with the temperature, all of that. The vertical lines on this graph show the wavelength that correspond to colors of visible light. We call that the visible light band. And notice we have our wavelength from around 400 to around 650 or 700 nanometers. Each curve is marked with a temperature marked in kelvins. So, if something is red hot, in other words, it is, well, let me go back to this graph. This kind of tells us that if something is hot, it emits light. So on this side of the spectrum, we have infrared. So as something starts to get hotter, it starts to glow more and more. At first, it's glowing in the infrared spectrum. At about 7,000 Kelvin, the object becomes so hot that it starts to emit wavelengths that are in the visible light spectrum. So think about an oven or a piece of metal. When you first get a piece of metal hot, it looks like a cold piece of metal. You can't tell that it's hot. Once it reaches a certain temperature, though, it begins to glow red, and then it begins to glow orange, and then it begins to glow white. So by heating up something, we can start to see visible light or starts to emit visible light. And if the material can withstand the heat, it can get very hot, and potentially it can begin to emit in the ultraviolet spectrum. So red hot is around 3,000 Kelvin. So if something is so hot that it's glowing red, it has very little power in the visible light band. So most of that power is in the infrared band, or the infrared. So it's emitting a lot of heat, if you will. So something with a temperature of around 3,000 Kelvin is going to glow red. White hot, so if I continue to take that piece of steel and continue to raise its temperature, is in the neighborhood of 5,000 to 6,000 Kelvin. So we have a lot of red, blue, and green. These colors, when mixed, make white. So the sun has a temperature of around 6,000 Kelvin. So if something is so hot that it glows white, we're talking about a very, very, very hot object. Now we come to blue-white. This is 7,000 plus. Some really, really large stars. They are so hot that they glow blue. So what we have here is there's a Color law that we can use. The wavelength of light will equal 3 times 10 to the negative third divided by the temperature. So where, lambda is the wavelength, and the temperature, now this is important, it must be in kelvins. So you can't use Fahrenheit or Celsius for this formula. But this formula right here will give us a way of calculating the wavelength of the light, or the wavelength of the electromagnetic wave being emitted based off of temperature. So there is a surprise in this law. Most people kind of think of the color red as being hot and blue as being cool. However, if you think about a flame, the hottest part of the flame glows blue hot, not just red. If you take a look at a flame, the inside is kind of white, and as you get towards the outside of the flame, it turns red. That's because the inside of the flame is hotter than the outside. So gas stoves usually give off a blue flame. Candles, a little bit cooler, give off a red flame. So one reason why we don't use a bunch of candles to cook with, it's just not hot enough. Potters can estimate the temperature of their kilns by the color of the glowing stones. Astronomers can use the color of stars to estimate their temperature. So the physics law behind this, or the physics behind this law, I should say, is that when things are hotter, the electrons shake faster. Shaking of electrons creates electromagnetic waves. So hotter electrons give a higher frequency because they're shaking faster. And then higher frequencies have shorter wavelengths. Now, when you're ready to purchase a home, there's many things to think about. One of them is the paint. Some paints are designed to absorb visible light but reflect IR. So what this means is that we can have a darker paint that would still keep a home cool. If it's absorbing the visible light, it kind of gives the paint a darker color because it's absorbing more of the frequencies. But infrared is kind of like the heat kind of wave. So if it's reflecting that, then it's keeping the home cool. And one reason why this is important is because roughly half of the sun's power is in the infrared spectrum. So roughly half of the electromagnetic waves coming from the sun are infrared. Now we can kind of calculate power or the wattage. One of the things that's pretty clear from all the plots I've shown you so far is that when an object gets hot, they emit much more radiation than when they are cool, or even kind of medium warm. So a formula we have for this is power equals A, forget what Greek letter, I think that's alpha, maybe capital alpha or something, T to the fourth. So A is for surface area. This is just a constant. T is for temperature in kelvins. So if something is twice as hot, it's going to emit 16 times more energy. Now the sun is around 6,000 Kelvin. And that's about 20 times hotter than the Earth. So if I do 20 raised to the fourth, gives me 160,000. So in other words, the sun is 160,000 times more powerful than the Earth. Which is one reason why it glows so bright. Going along with this, we can start talking about heat lamps and heat radiation. So remember that when we talked about thermodynamics earlier in the year, we said that heat flows, or heat is the flow of energy from one spot to another spot. And heat always flows from high temperature to low temperature. But heat flows in one of three ways: conduction, convection, or radiation. Well, infrared is the radiation part, so that's heat radiation. Suppose that we make a lamp that operates at about 1500 Kelvin to 2000 Kelvin. At that temperature, the amount of visible light is almost zero. There will be considerable infrared. And, these are what we call heat lamps. We typically use them in the food industry. The advantage is that you can warm something out without having a very bright light to distract everyone. All right, we're going to end the video here and pick it up with night vision.